Welcome to the VG Lab podcast, where we discuss engineering concepts and applications found in everyday life. Hello, welcome. My name is Eric Vazquez. I am an associate professor in the Department of Chemical and Materials Engineering at the University of Dayton, and I do this podcast as part of my teaching and research efforts. Today, we have the pleasure to host Mr. Fernando Vazquez.
Hi there, Dr. Vazquez.
Thank you for being here today with us. We're going to be discussing direct energy deposit metals, right? So some sort of additive manufacturing. So let's dive a little bit into it. What makes an additive manufacturing distinctive from other types of processing or conventional methods of manufacturing?
Yeah, so that's a good question to start off on. So there are seven main techniques associated with additive manufacturing. Direct energy deposition is one of those methods. Additive manufacturing essentially takes the approach of a bottom-up approach to manufacturing as opposed to top-down of subtractive manufacturing, which is what we typically see for conventional means. So with additive manufacturing, typically solid bodies are built layer by layer through the addition of material, either through a chemical means, a thermal means of bonding. Each additive technique has its own mechanisms of adding material. So, like I said, directed energy deposition allows for the production of very high precision solid bodies, which don't need a significant amount of material to be removed for post-processing steps through milling, lathing, et cetera, to get to whatever target geometry that you're interested in. You can really tailor your finished solid body to be within a few thousandths of an inch of whatever specification you have, and that's all due to again, whichever approach you use for additive manufacturing. Conventional methods are typically one of two categories, one being a continuous process or a batch type process. So think like in the steel world, you have continuous casters that just cast out from a certain lathe, a ladle full of molten solution of metal, continuously casting. That's one method, as opposed to additive manufacturing, which, like I said, typically focuses on batch processes. So direct energy deposition is a batch process where a target geometry is used to deposit material to whatever target geometry that you want. Yeah, that's additive manufacturing as a whole.
Very good. Yeah, it's definitely something that is growing, especially over the past few years. There is a term that I've heard that is Industry 4.0. So can you tell us a little bit about what is Industry 4.0 and what is the impact of additive manufacturing?
Yeah, I wanted to just touch on the impacts of additive manufacturing on the industry as a whole. The Industrial Revolution can essentially be separated out into four distinct periods at the moment. The first and second Industrial Revolution being the advent of mechanical devices, steam-powered locomotives were part of the first Industrial Revolution. And really hopping over the first and second Industrial Revolution to the third one, which is the period that most of us are familiar with. It is the point of history between 1950s to early 2000s where primarily analog-driven devices have been converted into digital instruments that are able to capture information at a higher fidelity with higher precision, allowing for the use of computer-aided design. Computer-aided design is really a fundamental touch point of how additive manufacturing is able to function. Same with direct energy deposition, where you can have your computer-aided designs of whatever specification or whatever geometry you want to print at, that allows you to take these models and apply it to whatever platform you're printing on for directed energy deposition, allowing you to have automatic path generation at that point. So with what I call, what some folks consider Industry 4.0, it's really the integration of digitally controlled processes and algorithmically derived decision making through pathing or parameter development. So artificial intelligence has been a big talking point recently in the last few years of development, and artificial neural networks can actually be introduced into the direct energy deposition process, like I said, to generate models for the melt pools being produced by the lasers, the mechanics of the material being fused to each other, and essentially allows for a large-scale automation to be able to be integrated into the directed energy deposition process. Again, all of these optimizations further improve or reduce the need for additional post-processing to hit whatever target surface finish you want, or to really tailor your microstructural characteristics of whatever metal you're being deposited in.
Okay, excellent description that you gave us. Can we go more about the process of making these metals or printing? So you talk on a term called directed energy deposition, right? Can you explain a little bit further on that?
Yeah, for sure. So directed energy deposition is a method that allows for the layer-by-layer fusion of material to make a solid body, as I mentioned earlier. Directed energy deposition typically is a process that entails a feedstock, either in a wire format or a powder format, being introduced to some sort of stream of energy, either through laser, electron beam, or plasma beams that's able to create a melt pool and rapidly melt the incoming feedstock material and able to produce these melt pools that are able to, like I said, melt your feedstock material and able to fuse to the pre-existing solid body. That process is typically used, directed energy deposition machines typically utilize a good amount of robotics with computer-generated pathing and controls. And it's once you have your parameter set up for directed energy deposition and a target geometry for whatever you want to print, it's essentially plug and go, other than a few process considerations to assure that your deposition is stable.
Very good. So why did you use this example to highlight the chemical processes of the materials?
Yeah, so with any metallurgical process, there's a variety of mechanisms and phenomena occurring inside your bulk material to be able to get a material with your desired chemical, mechanical, or electrical properties. In directed energy deposition, you have two main mechanisms that really impart major changes to the microstructure of whatever you're depositing. One being the incredibly high rates of heating and cooling associated with melting your material. It has been measured that the heating rate and cooling rate of the feedstock material can actually go up to about 10,000 degrees Fahrenheit per second of either temperature increase or decrease, allowing for a lot of thermally derived precipitates or microstructural development to occur at a very rapid pace as material is being developed. A lot of microstructures are heavily dependent on the heating and cooling rates that are associated with the said material to be able to develop different microstructures. Like an example for steels, if you have a very quick, if you take a piece of steel at an elevated temperature and quickly quench it with a water bath, you can actually induce martensitic structures, and I'll touch on this a little bit later on in this podcast. But yeah, these cooling rates really impact the mechanical properties of a material. And in some circumstances, if you don't have a tight control over your process parameters, such as the shielding gases or even the chemistry of your feedstock, you might introduce precipitation of other secondary phases that could be detrimental to the mechanical or chemical properties of whatever you're producing. So lots of chemical phenomena occurring inside the material as it's being deposited, and additive manufacturing is really a technique of numerous switches to be able to put to be able to control very highly controlled process to be able to get a final product that is essentially as void-free and defect-free as possible without, like I said, adding extra materials needed.
Excellent. Yeah, that highlights very well the different effects of the chemical structure changes, right? So in regards with in situ contamination, do you have any examples that you can give to us?
Yeah, I can definitely talk about that. Just as a quick highlight, diffusion is it's a temperature-dependent process. As temperature goes up, rate of diffusions typically increase. When you have a high-temperature melt pool located at the center of wherever you're depositing, it's typically shielded with argon gas as the shielding agent to whatever you're depositing. This argon gas typically prevents, say, trace amounts of oxygen in whatever environment you're depositing in from reacting with your melt pool and potentially causing any oxides that can have detrimental impacts to your properties. But it could also have some detrimental effects if you have a argon feed rate that's too high. What I mean by argon feed rate is most directed energy deposition heads have a center nozzle where either the wire or powder feedstock is sent through the deposition head, and then there are lasers that are attached probably an inch away from that center nozzle where the feedstock material is going, where these lasers are pointed towards your target area and are highly focused to about a 3 millimeter to 6 millimeter focus point, where you increase you try to maintain the highest amount of energy density to melt your material and be able to produce the melt pool that travels along and actually produces your solid body. If you have argon gas that is argon gas flow rate that is ideal, you're actually removing a lot of the vaporized material that is coming out from your deposition, as well as shielding away from any, like I said, extra contaminants from, say, trace amounts of oxygen in whatever build chamber that you have. And so there's not just oxygen that can come into play if, say, you have high amounts of moisture in your build volume. That can actually cause other secondary precipitates from form. That actually causes secondary precipitates to actually form in local areas in your build if you don't have adequate shielding gas to be able to prevent that from occurring. If, say, you have too high of a shielding gas flow rate, then you can actually push around and induce a little bit higher amounts of turbulence inside your melt pool, which can increase the amount of subsurface porosity that you can see on your build, or increases in surface roughness to your final product, just by having a argon flow rate that works against the viscosity of your melt pool that you have.
Very good. So we discussed a little bit about the processing, right? Can you give us a case study example of a certain type of metal that has been gone through the process itself?
Yeah, so I found a case study that was taking a look at a titanium alloy, Ti-64 in this circumstance, that was actually being deposited with a shielding gas chamber and an unshielded gas chamber, essentially controlling the amount of the amount of latent oxygen that's occurring in whatever build volume you have. And saw that this paper saw that when titanium depositions were occurring inside a shielded gas chamber, there was less oxygen being present in your build volume, which actually just naturally created parts that had that met the criteria for oxygen content. In the aerospace world and the medical world, the amount of oxygen concentration that you have in your final product actually changes the grade of titanium that you have, with some aerospace applications requiring significantly smaller oxygen contents than what you would see in the traditional world. So this paper found that without a shielding gas chamber, you were actually able to get about 2,000 parts per million oxygen content, while introducing a shielded gas chamber actually decreased that to about 1,300 parts per million. This study was only focused on the oxygen content of the final deposition. It didn't look at the mechanical properties, the corrosion properties, or the surface properties of the final finished part, but was just highlighting the effects of higher amounts of control to your deposition environment, how that downflows and gives you better oxygen content
Okay.
in the final part.
Yeah, that's important, right? So you also discuss some other aspects, right? Like the surface texture. My guess is that microstructure will affect the properties of the final material. So how is the microstructure affected by the temperature gradients present in the melt pool?
Yeah, like I mentioned a little bit earlier, in metals, the cooling rates associated with different processes significantly affect your microstructure. If you have higher rates of higher cooling rates during a deposition, you can actually impart some higher cooling rates can inhibit the amount of secondary precipitates and particles that can actually form inside your microstructure. Some secondary phases like your chrome oxide, chrome carbides can affect your wear resistant properties of your material, or in the case of some oxides, that highly controls your corrosion inhibiting properties at the surface level. So if, say, you had a... So let me take a step back. So you have the cooling rates and heating rates that are associated with the actual melt pool, but the amount of energy that you put into the melt pool can actually create latent heated areas, which can actually cause some sort of a natural aging inside your bulk product as you're being deposited. So you're fighting both the short-term phenomena and microstructure refinement inside the melt pools that heats up and cools down. But as you're depositing, as you're building up layer by layer, you actually still have that latent heat that is maintained away from the direct deposition area where the melt pool is, and can actually, like I said, cause aging in, say, aluminum alloys or other time-dependent microstructures that require some sort of heat to age. You'll be able to see some of those characteristics. In the case that I highlighted for this script, I actually took a look at a variety of... I found a paper that looked at the absorbance of laser light of two commonly used laser sources for direct energy deposition, and actually looked at the microstructural development of the martensite and the stainless steel. So martensite, like I covered before, is a microstructure that forms when you have a rapid cooling rates. In this paper, it actually investigated the morphology of the martensitic laths that form as they got developed, as more or less of an energy density was being applied into a deposition. So higher amounts of energy being put into the melt pool caused a greater temperature gradient, which caused the laths inside the martensite to actually be smaller than when you have less energy going into the melt pool.
Very good. So talking about steel now, right? How those steel produced through direct energy deposition perform differently to wrought steel?
Yeah, so in directed energy deposited steels, you can highly control the amount. You can control the paths and the parameters in a way where you can actually reduce the amount of porosity, voids, or defects that occur in the final product of whatever you're producing. The elimination of these voids and defects ultimately increase the mechanical properties of the steel that you're producing. With directed energy deposition, you can tightly control both your bulk products, being able to refine that microstructure, like I mentioned before, in smaller batches, as opposed to large-scale foundries or casting operations that have to look at the microstructure of a steel over coils that are about 2-3 tons in weight, as opposed to here where we can look at the microstructural development of a smaller volume of material being produced. So there's that. But another way where directed energy deposition also differs from your traditional cast or wrought steels is there's a large amount of compressive of residual stress that is actually formed inside your depositions as you have lines of rapidly heating and cooling melt pools. That thermal difference actually imparts, like I said, a residual stress that needs to be heat treated outside. That needs to be needs to have a heat treatment applied to the material in order to resolve some of those residual stresses. In some circumstances, those compressive residual stresses for like the cases of fatigue actually work to start closing up fracture initiation sites in like test samples. So this compressive stress in these directed energy deposited materials can benefit some mechanical properties while being detrimental if, say, you're applying a compressive load to a material that already has an intrinsic compressive residual stress to it.
Good. So can we go and perhaps discuss a little bit of the applications of this steel prepared using the directed energy deposited system?
Yep. So there are actually two different approaches that you can take when producing anything with directed energy deposition. You can either create new bulk products, creating completely new components just with the process itself, or another area of interest is actually repairing pre-existing products. So, for example, in the automotive world, there is a lot of dies and punches they could use while forging automotive parts. So, for example, some of these punches can last for, say, 10,000 uses or so. After a while, the edges of these punches start deforming just due to the amount of wear and overall use in the process. One can use directed energy deposition to actually take the same material that your punch was made out of and actually dimensionally restore your die or punch to the initial geometry, essentially being able to recycle that product and not needing to have a whole nother waste stream of recycling that die, manufacturing a new die, and all those processes associated with them. And you're not limited to dimensionally restoring with that same material. You can actually take various compositions or even other novel coatings and be able to laser clad coatings that are more wear resistant, impact resistant, et cetera, to improve the product from what you had initially. So there's a variety of approaches and a variety of uses of directed energy deposition. It's very interesting that there's always new formulations on chemistries for the feedstocks that can find new uses for directed energy deposition. There's a lot of spaces for direct energy deposition to work on as its own novel technology, but also being able to augment like the traditional casting or forging world to be able to replace and repair those dies, molds, and be able to work as a a sustainable technology. At the end of the day, that's what additive manufacturing really tries to work towards is how do we reduce the amount of material that we use? How can we make processes more efficient? And how can we further improve the processes and materials that we have to be stronger, more corrosive resistant, and just better than what we have right now?
Certainly, that ability to repair existing dies or balls, that definitely helps a lot, in particular with respect to pollution and waste materials, right?
Mm-hmm.
So that was a very great introduction to direct energy deposited metals. Thank you again for presenting on this and additive manufacturing, Fernando.
Yeah, thank you very much for having me.
Thank you.